Hi, welcome to this week's lab on determining an equilibrium constant. And so for this week's lab, what we'll be doing is, yes, you can go to YouTube, where you can watch a demonstration that we watched in class about the iron plus 3 ion reacting with thiocyanate to make iron thiocyanate complex. And this was a very, very light yellow color, or colorless, and we could watch the equilibrium shift from either right to left depending upon what color the solution was. So hopefully we've learned about equilibrium and Le Chatelier's principle by our lab that we had a week ago on Le Chatelier's. And so in looking at writing down the equilibrium constant for this reaction, we will get the following. And this is, of course, versus concentration of products over reactants. And we will, in order to determine this actual value, we will need to determine each of these concentrations at equilibrium. Okay. Now we can know what their initial concentration is. We can figure out the change, but our big thing is figuring out what are these equilibrium concentrations so that we can measure Kc. Now, in order to find the concentrations at equilibrium then, we are going to find or use the spec 20. And so we are going to be looking at setting our wavelength at 450 nanometers and measuring the absorbance of solutions of known concentrations. And so we first of all have to set up a calibration curve. And so with our calibration curve, we will have solutions that we know the concentration of iron thiocyanate, because we are going to force the reaction to make a lot of products, therefore the iron thiocyanate ion. And then we can then find the equilibrium concentrations using this calibration curve for our known solution concentrations. Now, in terms of our experimental procedure, there's two parts of this lab then. The first one is, of course, generating a calibration curve and preparation of your standards, measuring the absorbance of those and generating that curve. And then what we'll do is then we can measure the equilibrium concentrations of the iron thiocyanate complex versus different concentrations, initial concentrations of the iron and the thiocyanate, so that we can determine the equilibrium constant. Now, one big thing about this lab that is going to be major, okay, is the calibration curve concentrations for the ions are different than when we determine the equilibrium concentrations for our complex. So you need to make sure that you are getting the correct concentrations of solutions from the cart. If there are no more bottles of that solution on the cart, obviously you're going to have to walk around the room and see who has that bottle. All right. Now, we are going to have different concentrations of iron and the potassium thiocyanate. So make sure you're looking at the bottles. Okay, this is going to be your big job. And then we're also going to acidify this reaction so that we don't have any precipitate forming. Okay. Now, in your lab procedure, it will tell you that you're going to make up 5 different test tubes. Okay, and make sure that you are labeling them. And you want to be very specific if it's for the calibration curve or not, okay, because of course if you drop over dead, then I know what test tube number 1 is, because there will be a test tube number 1 in part 2 of this lab also, so I need to know which one is different. You will be adding water and make sure that it is DI water, and you'll be using graduated pipettes in order to do this. Now, what you'll be doing then is you need to make each of these 5 solutions, okay, and measure the absorbance of each of these known concentrations of solutions in order to generate our calibration curve. So we'll be measuring the absorbance using the Spec 20. Now, because we have such a large concentration of potassium thiocyanate, and essentially we're only using it to get to this ion, what it does to our equilibrium reaction is, because we have such a large amount of the reactant, we have too much of it, it does drive the reaction towards the product side. So we do know that when we're measuring this in the Spec 20, we have the maximum amount of the iron thiocyanate complex that can possibly be formed in this reaction. And so you need to calculate these concentrations, and you can do this before you even come to lab, so that when you plot it against their absorbances, you can generate the curve while you're in lab to see how linear your curve is. And so in order to calculate these concentrations, you have to use our stoichiometry, a 1-to-1 ratio. For every 1 mole of iron plus 3 ion, you will make 1 mole of the thiocyanate ion. Okay, and so we'll use that 1-to-1 ratio. So on the next slide here, whoops, I'll show you how to calculate that, because you can do that before coming to lab and set that up in a table. Make sure before you come to lab that you set up your lab so that you have a table of data. So test tubes 1 through 5, under calibration curve, you have a place to measure their absorbance or plot their absorbance, and then of course your thiocyanate complex concentration. Now to find the molarity then, notice that I have written down that I'm going to calculate the molarity of the iron thiocyanate complex. And so that will be equal to taking the molarity of the iron plus 3, multiplying it by our mole to mole ratio, and this will then get me moles of iron thiocyanate. And then in order to get to molarity, I can take the moles of iron thiocyanate complex and divide it by the total volume of the solution, of course, in liters, and that will get me molarity. So remember, when you're giving me a calculation page, you are writing down equations like this before giving me sample data. Moles of the iron thiocyanate complex would be this equation. So for us, we're going to have a total volume of solution in the test tube of 10 milliliters, or 0.10010 liters. Okay. Now, our volumes probably will go to 1 more decimal place with a graduated cylinder, a graduated pipette. And so then we'll multiply that by the molarity of the iron plus 3 ion that we are using for the calibration curve, because it is different than when we're doing the equilibrium. And then I'm going to use my mole to mole conversion from reaction number 1, which is just saying that our complex here only requires 1 mole of iron plus 3 to make it. And then, so that gets me the number of moles of my iron thiocyanate, okay, because here I would have to take this by the volume, sorry, of the solution. So now I have the liters cancel, the moles of the iron plus 3 cancels, and now I have moles of our complex. Now to get the molarity, I'm going to divide this, and over here, bad me. This was our 1 liter that we were pipetting into our test tube, so I apologize for that. And it did have 2 significant digits, okay? And so if we look back, so that was my fault. We were pipetting 1 milliliter of this iron plus 3 complex. So I apologize for that. So this is the volume that you pipetted in of just the iron plus 3. Then the total volume of solution of the entire test tube, if we look back, if we're looking, we have 1 plus 4 plus 1 plus 4. So our total volume is 10 milliliters. Okay, so 0.010 liters. So I've taken my moles of my complex divided by the volume of the solution, so it's the total amount of volume in my test tube. And what I get here in the end is 1.5 times 10 to the minus 8 molarity. And please tell me of what chemical? Of the complex. Okay, and so that would be my one example. I'm showing this for my calculation. Now you will have to make this calculation for all 5 test tubes. You only need to show me one example. Okay. Now if we go back to our procedure then, once we have made up these 5 known concentrations for our calibration curve, we want to make sure that our filter bar on our spec 20 is set to the proper position, and we of course will set our wavelength to 450 nanometers. Zero the spec 20 using water as a blank, and make sure you let it have a 15-minute warm-up. So as you get into lab, have one of you or your partner go get the spec 20 and start warming her up. Okay, and make sure that you condition the cuvette, because you'll have a cuvette for your samples, with each of your new solutions. So pour a little bit of your new solution that you've made up into the cuvette, swish it around, and dump it out into waste. All solutions today go in the aqueous waste jug. Okay. So you will want to set up zeroing the machine. So maybe one of the partners can start making the solutions while the other partner is zeroing the machine. But do not zero the machine until you've at least let it warmed up for 15 minutes. Now, once the machine is warmed up and all your solutions are made, all you need to do is put your test tube, okay, and remember we have filling that up to about halfway up on that circle that's in your cuvette. Put them in the spec 20 and of course record the absorbance. Dump that solution out into the waste jug and then condition it with the new solution, okay, and then put the new solution in and of course measure its absorbance. Make sure that you always zero between each sample. So make sure that you just recheck that the machine has zero absorbance with the blank between each sample. Then what you can do is that you can, if you have a graphing calculator or maybe you've brought a laptop to lab, you can just quickly determine if your calibration curve is linear. If it looks like one of your solutions is a little off, you may want to take time to remake that solution and again check the linearity of your regression line. Okay, now once we've made the calibration curve, so let's say this was my fake, and remember guys, this is fake, totally fake, okay? When you have done your calibration curve, and you might just do it on your calculator just to make sure it's linear, but you will be submitting a calibration curve with your report for the following week when it is due. Make sure that you have a descriptive title. And what I mean by that is we are going to be talking about what is measured on the y-axis versus what is measured on the x-axis. Versus does not have any punctuation. It doesn't have a little period, and it's little v, little s. And that every word of the title, except for things like of, the, are all capitalized. So in general, like here I have absorbance of various solutions of chemical X, whatever that is, versus the concentration of known solutions of chemical X. You do want to make sure you don't abbreviate any of the axes, write out the entire word absorbance, okay? Here on concentration, I want to say concentration of what chemical, and then of course in parentheses make sure that you have units. And in this lab we are measuring the concentration in terms of molarity. The other thing that you will need on your curve is of course do a linear regression. If you don't know how to do that, or you've forgotten how, make sure you stop by one of my office hours and ask me that question. But you also need the R squared value on your graph, and also the equation of the line, okay? Because the equation of the line is going to help you get your concentrations of your unknown solutions, because we'll be solving for X because we'll know Y. We'll know the absorbance of an unknown solution, and then we can calculate X. Now, part 2, the real meat of this lab. We are again going to have 5 test tubes. So you're going to have to wash out the test tubes you used in part 1. Okay, don't go and get any more because we don't want to generate tons and tons of dishes. Make sure you clean them really, really well. Now, you're going to be getting different concentrations, okay, of the iron nitrate and the potassium thiocyanate. Notice that my iron nitrate has already been pre-acidified by the lab tech. So I won't have to get nitric acid again. I can just take my pre-acidified solution. So again, make sure that you're looking at the solutions. Now, in terms of getting about 20 mils of each one of these solutions, make sure you're putting it in a beaker and make sure you're labeling it. Don't just label it with the chemical name, label it with the concentration also. Okay, so there is no question of which one you have. Then you will be pipetting, of course, various volumes of each of these chemicals into test tubes. Okay, each of the test tubes needs to be brought to a volume of 10 mils. And so you'll have to be using some DI water to bring that proper volume to 10 mils. Now, you can mix each solution, and as with the calibration curve, what you can do is you can put some paraffin on the top of your test tube and shake it that way. If you use a glass stirring rod, okay, and while mixing that, remember when you remove the glass stirring rod, you are kind of losing some solution. So just be aware of that, okay? And if you do that, make sure that you clean, rinse off that glass stir rod and dry it before putting it in the next test tube. Now, before I move on, I just want to go back here quickly to our graph. Make sure that when you're handing in a graph, you print an entire page. And in Excel, at least in Excel, you can either display the graph within the workbook. So you'll have, the columns of data, and then you'll have your graph in between all of that. I don't want that. You want to display this as an entire chart and print out the graph as an entire page. Okay, I don't want some little teeny graph. All right. Now, you should have a table of data set up for yourself before coming to lab, because again, this lab is going to have a lot of stuff going on and you want to have your lab notebook prepped. So we're going to have 5 different test tubes having various amounts of potassium thiocyanate, and we're going to be looking at what is the equilibrium concentration then of our complex, and we'll be able to get this from the calibration curve that you have generated. Now, you do not need to graph your calibration curve formally in lab. You can just informally do it on your graphing calculator, make sure it's linear, and move on. So you do need to record the absorbance for your calibration curves, and you will be measuring absorbance for your equilibrium data, so for part 2. Once you have those absorbances, that's all the data that you really need to record today from lab. Everything else is a calculation. Now, of course, if we want a total volume here, we've got 3 plus 1, so we know we would need to add 6 mils of water to this, and we could go down and calculate how many mils of water each one of these things is going to have in it. Now remember, this one is the 2.00 times 10 to the minus 3 molarity solution, and this one is the 4.00 times 10 to the minus 3 molarity solution. So these concentrations, again, are different than the ones from the calibration curve. Now, You will be reusing pipettes. So when you use the pipettes in the calibration portion of your lab, you'll reuse them here. Typically what I do is I will have a pipette labeled for just the iron, okay? And just the thiocyanate, okay? And so I only use the thiocyanate in thiocyanate solution, and I only use the iron in iron, because if you accidentally use this pipette in this solution, you're going to start to get a reaction, and of course you'll contaminate your samples. Now, after you have measured the absorbances of all of your solutions here in part 2, then you're done. All of your solutions, the cuvettes, use a minimum amount of water to be rinsing those out and put that one rinsing in the waste jugs. All your solutions will go into the aqueous waste jugs. Use only a small amount of water to rinse out your beakers where you made up the solutions, rinse it and put it into the jugs. We don't want to generate a lot of water washing waste because, again, it would generate a lot of waste. These big jugs then, if everyone on your bench is done, put them up in the front sink by where I have all of my things so that it's just easier for the lab tech to deal with the waste. Please refill your DI water bottles before returning them to the cart. Physically hand in your cuvettes to me because I want to make sure that they are not left in the Spec 20s when you return the Spec 20s to the cabinet. Wind the cords around your Spec 20 nicely and put them back in the cabinets. You know where the Kim wipes go. You got them from there. Please return them to the cabinets, and any little Kim wipe garbage that you leave in your hoods or on your counters, please make sure they make it into the garbage can, not on the floor next to it, into the garbage can. And then, of course, I will take your stapled carbons up by my desk before you leave for the lab. Each person in the partnership must have data in their lab notebooks. Then, of course, we are going to enter data, and it's only from one person per partnership. So you'll decide who's going to enter the data into Google before Saturday at 11:59 p.m. Now, as we have seen on the last labs, entering erroneous bad data into Google because you were desperate on Saturday night and you had not really sat down to look at your lab yet, erroneous submissions will lose points, okay? And this can get very costly in terms of losing points because I am going to be calculating what answers you guys should be getting, and if your answers don't match mine, points will be taken off for you calculating your data incorrectly or entering it into Google incorrectly. Now remember, if you realize you've entered something incorrectly into Google, you can go back and resubmit before the deadline. Now, if you don't trust your partner, you can also go into Google and see what they have submitted. And so if you decide that you don't like what they have submitted, you can resubmit data, okay? Now, calculations. We've got lots of calculations in this lab, okay? And what I'm going to be doing for these samples is, of course, using fake data. So none of your data is going to look like my data, guys. So just please be aware of that. So we actually have 5 steps in order to calculate data in order to find the equilibrium constant. And this is for determining the equilibrium constant, K. Okay. And so once we find K, we'll be able to find it for every one of our test tubes, 1 through 5, and then of course we can find our own mean. Now we will also then have you look up what is the equilibrium constant for this reaction number 1, and you need to look for it online. And once you find it, cite the website and where you found it, okay? This is kind of like a Sherlock Holmes kind of investigative job, okay? It is not going to be as easy as typing it in and finding it on Wikipedia in about 2 seconds, okay? This is going to be your task. You must find the literature value of the equilibrium constant for reaction number 1. This reaction has been done tons and tons of times, but it is not readily available where the equilibrium constant is, so you're going to have to look. So what I've done here is I've set up a table for my results. These are calculations that I am doing. You do not need to have this table pre-written out in your lab notebook because you will not be doing any of these calculations during lab. Now you may want to have this table in your lab notebook for later so that you can utilize this information for, let's say, a lab quiz at the end of the term. So what I'm going to be doing is looking at how to calculate each one of these things, because essentially what we are looking at is we are looking at icing this particular system. We know or will know what the initial concentration of everything is, and then we are going to want to determine the equilibrium concentrations of everything via the calibration curve. Okay, because again, we will only find equilibrium concentrations via your calibration curve. So I'm going to look at the steps 1 through 5. Now this is just reiterating what is written or typed up in your lab procedure, but I just want you to know this is how we're going to do it. Now this, of course, is not indicative of your results. I have used fake data. Now, for example, it says each solution we're going to use 10 mils, and the molarity of each solution is 2 times 10 to the minus 3 molarity. And so in order to find out the initial number of moles of iron, I will take my 10 mils, or my 0.01 liters, and multiply it by the molarity of the iron. So notice here, I have defined what my equation is, I've put in my sample data, and I have come out with an answer. Okay, and again, I have told me of what am I measuring here, and it's iron plus 3. Please realize that iron nitrate is the same thing as iron plus 3, because it is a 1-to-1 mole ratio, and the nitrate is just a spectator ion. I'll do the same thing for the thiocyanate ion, taking the molarity times the volume. And so I had pipetted out 10 mils of this concentration. This is my initial number of moles. Now step 2 is finding out the number of moles of product that are going to be formed. And so what you need to do is you need to look at your calibration curve. So you will look at the absorbance of, let's say, test tube number 1. Okay, we're just doing this for our fake test tube number 1. So you'll have your y is equal to mx plus b. So you will plug in your absorbance of test tube number 1 in for y, and you will calculate what x is. And x here will be the molarity of your complex, okay, at equilibrium. So let's say in my fake data here, I found that after measuring the absorbance of test tube number 1, I found that from the calibration curve that the molarity of the complex was 1.5 times 10 to the minus 4 molarity. So what I would like to do is find out how many moles of product that is. So I'm going to define my equation first. So the moles of the complex will equal the molarity of the complex found from the calibration curve, and again, mine's fake, times the volume of the solution. And so here, because I mixed 10 milliliters of the iron plus 3 and 10 milliliters of the thiocyanate initially, I will have a total volume of 20 milliliters. And so multiplying the concentration of my complex times the total volume of the solution in liters gets the number of moles of the complex at equilibrium. Now, what we will find is that it is a 1-to-1 mole ratio, and so we're good to go on all of that fun stuff. And so we could then find the concentrations, okay, of the iron at equilibrium and the thiocyanate at equilibrium also, okay, because it is a 1-to-1 mole ratio. Okay. Now, finding the number of moles of each of the reactants present at equilibrium. So here's my equation. The moles at equilibrium are the initial moles minus the change. How many moles have actually been used up? Now, what we will find when we ice this thing, if we were thinking about icing, normally our initials are in molarity. We're doing it in moles, okay, but then we're going to have to go back to molarity when we're all done. But remember, our iron plus 3, and we've got our thiocyanate, each one of these will decrease by X amount, okay? So that we'll have our initial number of moles minus X, our initial number of moles minus X, and then, of course, we'll have our complex, sorry, running out of space, and of course, we're going to be making X amount of that. And so the number of moles of product that we made right here from the previous slide, 3 times 10 to the minus 6, that's what we just found right here. That is X. That is going to be subtracted then from the initial number of moles of each of our reactants. And so this is the amount of moles of each of these left at equilibrium. Okay, and again, I have defined my equation, and I just need to show one of the examples. Okay. Now, what I can do then is we found the concentration of the complex directly. This was from the calibration curve. Okay. Now we can look at finding the equilibrium constant. We need to get the molarities of each of these compounds at equilibrium. Well, we already have this one, so yay! Now we do need to get the ones for the iron and the thiocyanate. So we're going to take the moles of iron plus 3, and that is, again, at equilibrium. Okay, so back here we just found that at equilibrium. So we're going to take that number, and we're going to divide it by, again, the total volume of the solution. We used 10 mils of each, so our total volume of our solution was 20 milliliters, or 0.02 liters. So we will find the concentrations of each of the reactants at equilibrium. And this is, of course, their molarity. Now all we have to do is plug them in. We got this directly from the calibration curve. We got these from looking at what was the initial concentration, and now what is the equilibrium concentration. So we had to calculate these. Now, in plugging those in then, this is the equilibrium expression. By plugging our molarities in, we get 208. And again, this is fake. So I have now found the equilibrium concentration for test tube number, the equilibrium constant for test tube number 1. So we will need to go back, and we've just got 208. You must do this for all 5 test tubes. You may want to set up an Excel spreadsheet that can do this calculation for you, or just manually do those all by hand. Either way, it will work for me. Again, you only need to show one example of each one of these calculations. All right? Now, what I've proposed in this lab is there is actually no reason to believe that reaction number 1 is actually the reaction that is occurring in the test tube. What if it was this reaction, equation number 4? Well, what we know is that in an equilibrium system, the equilibrium constant remains constant when we start with different amounts of the reagents. Because we know that, looking at those equilibrium curves, we are going to get a certain ratio of product to reactant. But if equation 4 is occurring, and that's the real equation, their equilibrium constant that we calculate for this scenario should also be constant. So you can't have one or the other. You have to have either Kc being constant for reaction 1 occurring, or we would have the equilibrium constant for reaction number 4. And so part B of this lab, and you'll be doing these calculations at home, are going to actually definitively answer this question, hopefully. So in part B, when you're reading through your lab, it's going to go through the scenario of what if this reaction is actually occurring. Well, if you write down the equilibrium expression for this reaction, so I'm going to write this down, it is actually saying here, we're making a different complex. You'll notice here that for every 1 mole of iron, there are 2 moles of the thiocyanate. And so you need to square it, whereas for equation 1, we didn't have that. So what we'll do is when you're filling out this table, and we're only going to do it for test tubes 1, 3, and 5, when you're calculating your initial moles, these numbers will still be the same, but the equilibrium number of moles are going to be different, okay, as well as the equilibrium concentrations for the thiocyanate, which of course in the end will get us different Kcs. Now, if these Kcs vary a lot, then equation 4, this reaction, does not occur. Now, so you're going to be doing that data results, of course, for me to prove that this does not occur. So what I want to do in adding here is I do want part B calculations to be handed in after your graph. Now on the report sheet that you'll be printing out from Canvas, this is not included right here. By listening to this video and taking notes, you will know that this is the order in which this needs to be stapled in. So stapling the report form number 1, calculation pages number 2, second in our packet, our calibration curve number 3, part B table with her calculations just right on those printout pages, okay, right there. So if you look at your lab procedure, let's look, I'm turning to my pages here. This would be page number 7 of the procedure. Again, page number 7 of the procedure. Just print out that page and hand that page in after your graph. So right now, report form, calculation pages, calibration curve, page number 7 from the lab report, and then of course your post-lab question sheet. Now, you will need to submit your data before Saturday, May 9th, before the 11:59 p.m. cutoff. Now, here on the report sheet, make sure that you're including units on all your data and beware, of course, of significant digits. Now, you're going to be calculating your mean equilibrium constant, and this is for part A of part 2, okay, for equation number 1. Okay, there are going to be no units on any of those equilibrium constant values. I also want the class mean. Now, I've given you some space on your report sheet. You can remove any outlier data points that someone may have submitted. So let's say your equilibrium constant, mine was 208. Okay, again, it was fake. And someone submitted 2.8. Probably an outlier if everybody is around in the 200s. So please tell me which data points you removed when calculating your mean. Okay, so you can just list them out and say, these are the data points that I decided were outliers. Then you will need to calculate the class standard deviation. And again, that equation should be in your calculations, but then you can say your calculator calculated it. But please define again the terms in the standard deviation equation and also the mean equation. Now you will be doing a percent error, okay? And this is between the literature value, and this is found from a website, okay? And you're going to be taking the literature value minus the class mean, okay? I want to see what is the percent error there. And of course, there is a place on your report sheet that cites the website. Please give me the full address of the website where you have found this magical data. So again, just to reiterate, the order, whoops, report form, calculations page, calibration curve, page number 7 will come next, and that's the Part B table with its calculations just directly on that page. And then your post-lab question sheet. Please make sure it's stapled in this order and double check on your carbons for your calculations pages that they are in numerical order and it's easy to find your calculations. On your calculations, please number the calculations. Tell me what the equation is calculating. Of course, define all terms in the equation and show me only one sample data. Now, in your post-lab questions, you can show your work directly onto the page from the lab notebook. So you can be writing your answers in here. Just make sure that you can write, all right, everything in this column will be in moles. Everything in this column will be in moles. Otherwise, you're going to have to write moles every time that you do this within the box. Over here, make sure you're telling me these are in molarity. Okay? So show your work. You can use pen or pencil. I don't care on the post-lab questions. But remember, significant figures count and units count. And showing all work on the post-lab questions will also count. So hopefully that gives you an idea of what I would like for this lab report. Now, for the lab, again, you will get points taken off if you enter erroneous data into your Google Doc. So be careful when you are doing your calculations. You may want to email or text your lab partner so that you guys can see what they got as their results. Now, you may not agree with your partner. That's fine. Okay. But if that is the case, you will need to submit your own Google Doc. Okay. But I want really only one submission from each group. So please try to come to terms with who is right and who is wrong, because then it is much less data for me to actually look at and calculate, because this lab has a lot of calculations and I'm doing it for 50 people. So try doing your lab 50 times over. Okay, so thanks a lot for listening. I'm hoping that this discussion helps you out. Go back and look at calculations again if you have any questions, but I think that this lab will be a great one. All right, I'll talk to you later.